Hello, friend. My name is Derek Harder, and in this video, we're going to continue looking at processing text for doing text processing with deep neural network systems. So we're going to look at in more detail the two basic approaches for representing groups of words for a machine learning system to do natural language processing. So the bag of words approach versus the sequence models approach. Okay, but before we do that, we're going to go into a little bit more of a realistic text vectorization example. So we'll revisit the IMDB movie review data set, but actually show vectorizing it by hand. Okay, you ready? Let's go ahead and begin. Okay, so a little bit more about the two approaches for representing words for natural language processing models. So how to represent individual words is relatively uncontroversial. So, they're categorical features, right? So multi-class categorical. So we just assign an integer index and we vectorize those. So we encode those indexes as dimensions in some high dimensional feature space. So the more problematic question is how to encode the order of words, so the way that words are woven into sentences or their word order. So unlike other time series in natural languages, in most natural languages, the word order means something, but it doesn't mean everything. Okay, so order is important, but its relationship to meaning in natural languages isn't straightforward. All right, so the simplest approach for building natural language processing models is just to treat the words in a sample as an unordered set. Okay, so that's again the bag of words model that we introduced. So in this video, we're going to look at treating natural language samples as bags of words, and we'll also look at sequence models. Okay, so that's the other way is process the words strictly in the order they appear, like the steps in the time series. Okay. And then our next video after this one, we'll look at what's known as the transformer architecture, which you can kind of think of as a hybrid approach, where it's kind of fundamentally a bag of words, but there's a way to interject word position information into representations when you're using transformers. Okay, so but before we look at these two different approaches and build some models with each of them, let's return back to the IMDB movie review database. But this time we're going to actually download it by hand and show an example of text vectorizing it using the Keras tools that we looked at and using the data set to flow the data into the models that we want to build. Okay? So as usual, this is too big for me to put into the repository, so you'll have to download it. So curl is a similar tool to wget. You should have either of those. We're going to use wget as well here. And if you extract it, you'll find that it's actually 433 megabytes, but you can remove this directory. We don't need this. There's quite a bit in there. So after that, there's really only about 255 megabytes if we look at that. So we're actually going to prepare a validation set by hand. So all this code is doing here is it's copying 20% of the files at random from the test neg and pos subdirectories and putting them into a new subdirectory called validation. Right, so I already ran this, but if you run this and take a look at your directory structure, so for example, this was after I'd done those things. So the size is 259 megabytes after you unzip it and you remove that directory that we don't need. And after you run that one, there's a new, so originally there's only test and train data, so there'll be a new subdirectory under there that has the same structure for the validation data that we're going to use. So just as an example, you can look at any of these. They're plain text ASCII files in here. So like if you use the cat tool from the command line, we can look at one of the positive train reviews if you want to get an idea of what's in there. So let's go ahead and set up just one of those data sets, so the Keras data set. So this will stream this in. So we have one for video, there's one from text, but it expects a similar directory structure. So since we have two subdirectories called pos and neg, it'll create two classes for this data, positive and negative, as if it's a binary classification task. So our sentiment analysis here is kind of a binary classification for positive and negative reviews. So it's a good idea to confirm that we read in 20,000 files from the train, 5,000 from the validation. That's the result of taking 20,000 of the original training files and moving them over to validation, and then we've got the full 25,000 in the test set after we do that. So once those load, you should get those numbers if everything is right. So again, these work like an iterator. So this is actually going to be pulling in the raw text as objects, though. So these are going to be strings that are coming in here. So we'll have to have one of those text vectorizations in order to actually get it vectorized. But right now, like for example, if we pull in the first item from the data set, once this is finished here, so it yields TensorFlow strings. So you've actually got the full string. So this was the first one. We shuffled these or not that we pulled out of the training data, and it has a there it is. So it has a target of 0. So it assigns 0 or 1 to negative and positive in this case. Okay, so let's look at our first approach. So let's build some models where we will treat the samples as bags of words approaches, okay? So we're actually going to do the same thing that we did before. So we're going to use single word unigram encodings for our samples. So, so this is the same thing that we did before. We will have to do all the steps that we talked about to assign integer indexes. And then once we do that, if we keep the top 10,000 most frequent words, we will encode a vector that's just 0 or 1 using a multi-hot encoding, where 0 indicates that that word index was not in the review, and 1 indicates that it was in the review. So okay, so let's process this data using the Keras text vectorization that we looked at before, okay? And we're only going to look at unigrams, so that's the default here. We're actually going to use the 20,000 most frequent tokens instead of 10,000 that we used before. But we want to get things out as the same kind of a multi-hot encoding. So we end up with a vector with 20,000 features that are either 0 or 1. So we actually need to adapt that. So we need a one of these data sets that will only return the input. Okay, so this mapping is a little special kind of trick, but it will. So whenever you normally call the trained data set that we had here, you would get the input and the target, right? So here we'll only get the input so that we can do that adapt function that we talked about before. So this will build up our word index. So this will actually get all of the samples and normalize them, tokenize them, and build up our word index. And then once we've done the adaptation, you can call text vectorization on another sentence, and it will return the multi-hot encoding. Okay, so we set up so we further add on. We're adding on to the original one that's bringing in a string. So it brings in a string. This is like kind of chaining together data sets. Okay, so we'll first bring in the string, and then when we call it, it's going to do another mapping function here. So we will get the string and the label, and we use our text vectorization instance here to create that into a multi-hot encoding. Right. So the result will be that when this pulls out batches, you get batches with the multi-hot encoding and the label that you want. for the training data, validation data, and the test data. Okay. So let's make certain this is working. So again, make certain that you're clear of what these sequence of the data sets are doing. So for example, if we ask for the first input and target from the binary 1 gram, we'll get a batch. Our batch size was whatever we specified. Oh, was it probably like 32 or something? Yeah, so 32 up here. Okay, I'm just gonna is carrying through for all of these. So notice that our first batch that we get out from calling the training data set is we get 32 samples. Each one of the samples has been coded into one of these 20,000 multi-hot encodings. And our targets are the targets for all 32 in this batch here. So we get, since it's essentially a binary classification, doing the centum analysis, we get ones and zeros here. Okay, so let's try our first model. So we're going to be using this model. We're going to be changing the kind of the representation of the data. So, for example, using some bigrams and stuff. But we're just going to use a basic dense model to see how well it can be trained on this sentiment analysis data set that we have. Okay, so again, this is pretty much the same as we did before, with a few differences. So we increased the max size of the words. We're doing some regularization here with some dropout, but it's mostly the same. So let's go ahead and train our first model and see what we get here. So that shouldn't take too long to train. We just had 10 epochs here. It's a relatively small model. The data is, I mean, we're passing in vectors that are pretty big, 20,000 sparse vectors here. So you should see normally you'll get about 89% on your test accuracy. So I won't show the learning curves here. So again, if you compare that, it's probably a little bit better than we did before. The model we did before was maybe overfitting a little bit, so the dropout might have helped a bit. And we did use a little bit of a larger vocabulary, so that might explain some of the increase here. So remember, this is a completely balanced two-class classification data set, so a naive approach would just always guess either positive or negative and we get 50% right? So, doing pretty good to get 89% here. It's doing something. Although, just as a note, it's kind of known that, if you really optimize your approach here, you can maybe get about 95% test accuracy on this data set here. So yeah, just in summary, besides the other thing that we did change here is you did do the text vectorization process on your own here instead of using the one that was prepackaged for you in the Keras data sets. Okay, but so we got the data and did these examples of flowing it through the dataset objects to do the to encode it as a 1 gram bag of words, basically. Okay, so of course, discarding the word order like we just did is very reductive. So lots of terms, if you use a bigram or trigram, will end up as tokens that might help with the modeling, reasoning. So here, we're not going to change the model, but let's change the representation. So we'll vectorize using a bigram approach. Okay? So the text vectorization actually does return, if you ask for bigrams, we'll return all the 1 grams and 2 grams from the results. Okay, but that's so pretty much all we're changing in this example is we'll go up to using bigrams. So we'll use all the possible 1 grams and bigrams, right? And so that happens when you pull out this layer. For example, when we redo the adapt here, we're going to be getting a dictionary that has unigrams and bigrams. Okay, so potentially a much bigger dictionary. Right? But besides that, so it might take a moment to complete here. So yeah, just to make it clear here, since we're using bigrams, we can look at the vocabulary dictionary that's created, and you'll see if you look through this that you get a mixture of some unigrams and some bigrams in there. Right? So these will be in no particular order, but you should see, some places you'll see lots of unigrams, but other places you'll see mostly bigrams if you look through the dictionary. So let's test our model out again, but with the bigrams and see what kind of result that we get. So I don't always get a complete 1% improvement over the unigram approach, but you usually do get a little bit of an improvement. So that might be some evidence that this local order might be helpful. Right? So I might try actually reducing the what we keep. Right. Although it's a little kind of tough to judge here because we're keeping 20,000, but you have to remember the vocabulary became quite a bit bigger now with the bigram. So I might have to check that, test it out. I could even go up to trigrams and try that. So our bag of words representation, whether it was unigrams or bigrams so far, was just using a multi-hot encoded vector that was a binary vector. So everything was either a 0 or 1. So the term was present or not present. So, there is a way to actually get the count. So, for example, if a movie review contains the word terrible 3 times, instead of having a 1 for the index for terrible, you would get 3 if you ask for the count. Okay, but we haven't really addressed normalization in terms of text processing. So, small common words like the, a, is are going to dominate sort of the histograms, right? So what you'll see is these counts. If you do raw counts, you'll get big counts for the and a, right? So those seem kind of important. So you really have to normalize, but doing the mean centering and divided by standard deviation doesn't work when you have sparse vectors, since almost everything is 0. So it's common to use this term frequency inverse document frequency. So it's relatively easy to understand. We're basically counting up the frequency of the term in our sample, so the frequency of the term in our movie review, and dividing that by the frequency of the term in the document. Actually, dividing it by the inverse. So you take the log of the frequency of the term in the document. So this is a type of normalization. So the result is, at this point, all you really have to understand is the result of doing this TF-IDF normalization. Is that small words, since they're really frequent in the document, won't get very large numbers when you do TF-IDF, right? So remember, it's kind of like doing a count, but then normalizing the count. But infrequent words, if they're used more than is warranted in a particular document, will get a large count when you do this TF-IDF normalization. Okay, so the effect is it's kind of a measure of the importance of a word, right? So how important the word is in this sample document relative to how often the word is used throughout the corpus. So that's the way to think of it. So you probably won't see an improvement in this case, but this is a pretty standard normalization technique, and in lots of different situations it will improve performance when you're doing bag of words, natural language processing models like this. Okay, let me go ahead and just fit the model and just show you that it will get about the same performance as we did with the last 2 models. So one final note before we leave this section here. In the preceding examples, we did the standardization, splitting, and indexing using a dataset pipeline. So that was actually being done before. So those were the things, the data sets that we passed into our fit method. Okay. So the first layer of the model was actually expecting the vectors that were already vectorized. So if you want to actually use this in like a production environment for inference or prediction, you need to have something that will take a string as input and put it through the same vectorization before it feeds it into the model to make it inferred, right? So that's easy to do in Keras, and that's what the text vectorization layer does. So our instance of the text vectorization is what we were using for the fit methods. So we just reuse it. So we're guaranteed we're doing exactly the same standardization, tokenization, and indexing In fact, we're already using the adapted index here. We're not recreating a new index, right? So it'll use that index for these inputs, and the result from this first layer, so we have an input that's just expecting raw strings. The result out of that will be the same vectors that we should be getting. So in this case, we're still using the bigram. We're using the last model that had bigrams with the TF-IDF. Okay? But that will allow us to infer. So, if we pass in like a batch of 2 input texts, it will give predictions for us about, whether it thinks it's likely to be a positive review or a negative. You see it. It worked because we are getting 90% accuracy on our accuracy measures, or close to that on here. So you can pick out words like excellent, I loved it, and awful here, and give you high or low ratings on a positive. Okay, so that's going to be it for this video. I'm going to wrap it up and we'll continue with the sequence models in the next video. So just to summarize what we've done so far, so we talked a little bit about the 2 basic ways that you can process text. So 2 different ways you can treat word order. So in this video, we concentrated on the bag of words model. So in bag of words models, you're basically discarding order. We're going to treat the data as an unordered set. So typically what we'll end up doing is encoding a single sample as a multi-hot encoding, right? So in our example here, since we use the 20,000 most common words in a vocabulary, we ended up with for every input sample, so for every movie review, we had one 20,000 item vector that was sparse encoded and that had 0s or 1s depending on if that word appeared in the review or not. Okay, so we also talked a little bit about ngram, so bigrams and trigrams. So that could be useful. So bag of word models are inherently, they don't have keep any information about the order of the words, but the order of the words can help. So you can try adding in like bigram or trigram to your vocabulary. That might help. The other thing that we looked at is we used the TF-IDF encoding, which is kind of a way of normalizing the data. So instead of just taking the counts, so if somebody said this review was terrible, 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 and you use the raw counts of 4, that doesn't work as well as doing some normalization. And TF-IDF will actually normalize the words. Also, it will handle like little words like a and if. So if you do a count like that, you'll get really high counts for common words, which will kind of destroy the information. All right, so it's very common to use that TF-IDF to normalize, and it will emphasize the importance of where it'll pretty much just make zeros small words, even if they're used a lot. But if you use more rare words, if you use them more frequently than normal in your text sample, they will get kind of a big value. All right, so that's it for the bag of words model. So hopefully you'll come and see our next video where we'll continue on with the discussion and look at how you use sequence models.